All right, we're going to do problem 37. And typically, or historically, I guess 37 is one of my favorite problems. So it goes, the strength of a rectangular wooden beam is proportional to its width times the square of the depth. Find the dimensions of the strongest beam that can be cut from a 12-inch diameter cylindrical log. And there's two other parts to the problem, and I'm not as concerned about those two parts. This part A is the part that is the part that's concerned, the part you really want to know how to do. Okay, so I've got over here a picture of our log, and the strength is proportional to the width. So we've got a rectangular beam kind of being cut out of here, so we'll call that the width. And then the depth goes this way. And again, you always zoom in on what do you want to maximize or minimize. We want the strongest beam. So let's write an equation for strength. And it says strength is proportional. So that means you're going to multiply it by some constant. And it would depend on the wood. Hardwood might have a stronger or a bigger constant than a softer wood, but some kind of a constant that's just going to factor through our problem. So strength is proportional to the width, so some constant times the width, and times the square of the depth. So times the depth squared. So immediately in the problem you can see, oh wait, depth counts more than the width. So it's probably going to make sense to not have a square beam cut out of this, but something that's probably taller than it is wide. Okay, we want to take the derivative, but again, we notice we have two variables. W, our width, is a variable. The depth is a variable. And keeping in mind, K is just some proportionality constant. So K is a constant. Maybe we'll just make a note of that. K is a constant. All right, so first slightly clever thing is we need to figure out how W and D relate to each other. And so we look and we notice it was a 12-inch cylindrical log. And you typically would draw a diameter maybe horizontally, maybe vertically. But if you do that in this problem, it doesn't help a whole lot. Let's just take that off. And instead, it will help a whole lot more if you draw your diameter right through, right along the diagonal of your beam. And that is also a diagonal, so I can label that 12. And that's the diameter of my log. If we draw it there, and I think the book already drew that picture that way, so maybe that wasn't such a trick. But that's our diameter. And as soon as you draw that, you know it's a rectangular beam. So we've got a right angle there, and you're thinking Pythagorean theorem. So W squared plus D squared equals 12 squared, which is 144. Now, we look to the right at our equation for strength. Do you want to solve for W or do you want to solve for D? And since we notice in that equation D squared, it'll be a little easier just to solve for D squared. So D squared is 144 minus W squared. If you did it the other way around, you've set yourself up for just a little more work. So S equals, I've got this constant connected with multiplication, which isn't going to affect our critical points at least. I've got W, and then D is 144 minus W squared. I'll distribute, so my strength is constant. I can keep that out in front. I got 144W minus W cubed. All right, I want to maximize strength. To maximize or minimize, I'm looking for critical points. I will take the derivative. The constants connected with multiplication factors through, doesn't really affect the problem. In terms of critical points, I get 144 minus 3W squared. I'll set my derivative equal to 0. And again, ignoring the constant because we're assuming it's not 0. That would be a wood with no strength. Oops, don't need another equal sign there. So 144 equals 3W squared. Divide by 3, and that gives us 48 equals W squared. And so we take the square root, and we get the square root of 48, which is 16. So it looks like 4 square root of 3 equals W. Let's go back up and read the questions and make sure we're answering it. And find the dimensions of the strongest beam. So we've got the width. And again, our units would be in inches, because right here it was a 12-inch log. So 4 root 3 will be the width. And let's see what the depth is. Oh, look right here. There's D squared is 144. W squared, we had it right here. So minus 48. So D squared equals 96. So if I take the square root, I'll take the square root of 96. 16 is still a factor, so it'll be 4 square root of 6. So my dimensions are 4 square root of 6 for the depth. So that equals the depth. And 4 square root of 3 equals the width. We should make sure over here, when we were taking the derivative, this part here, that we truly found the maximum strength and that inadvertently we haven't minimized the strength. So let's use our second derivative test. We'll come down and take the second derivative. Again, the constant factors through is multiplication. It looks like minus 6w. So when you sub in your w, surely for the second derivative you get a negative value. Our second derivative is negative, and so when w equals 4 square root of 3, we found our local max by the second derivative test. Okay, and that completes our problem.